Sure.
Professor Limay. Hello, sir.
Hello.
Hello. How are you, sir?
Very well.
Good afternoon, friends. So it's a great pleasure for me to introduce our speaker, Professor Luigi Accardi from University of Roma, Tor Vergata. He is a renowned researcher in the field of quantum probability. Uh, he is the managing editor of the journal Infinite Dimensional Analysis, Quantum Probability and Related Topics. He is the editor of the book series on a book series on quantum probability, which has published around 32 volumes. So the quantum probability community owes a lot to him. So today he is going to speak on quantum probability, a short historical survey of the main new ideas.
Thank you very much, Santano. I'm very glad to have this opportunity to give a talk in IIT Bombay, which is a very prestigious institute, well known all over the world. I'm glad that there is, in the audience, there are several younger people. And this is an institute of technology, but nowadays, high-level technology badly needs combination with high-level science. In particular, probability in the last 50 years has undergone a true revolution that can be compared only to what happened in geometry 200 years ago with Gauss and then Boyle and Lobachevsky and so on. I will try to summarize in a little bit more than 1 hour a development that took place in, roughly speaking, 50 years. So for your, I want to anticipate a kind of index of what I'm going to say, because the events and the issues to be dealt with are many, and I will have to rush a little bit. So I have tried to divide and to single out the main steps that have gone in this radical change of our view about the laws of chance and their mathematical model, which is probability theory. So the name quantum probability is an historical name. A more precise name should be algebraic probability, because algebraic probability synthesizes both classical and quantum. And there are many other possibilities, as you will see in the second part of my talk. the first step towards the understanding that we are not in presence of a single difficult problem, but of a radical change of point of view, came from a very well-known branch of quantum theory, which is known under the name Foundations of Quantum Theory, and has to do with a lot of apparent paradox. I insist on the word apparent because now we know they are just an historical remnant. But now we understand very well there is no paradox. So once we have understood that the paradoxes of quantum theory come from the mixing of two models, two mathematical models of probability, then the next obvious question was, if there are two models of probability, like there are many models of geometry, and the mathematical models are totally different, as you will see, then since a model follows from the axioms of this model, there should be at least one axiom in classical probability that plays the role that historically the parallel axiom played in geometry. Which is this axiom? Then, once you have individuated, and we will see in a moment this hidden axiom in probability theory, the next step is, can we do for probability what Hilbert in the beginning of the century, the 20th centuries, did for geometry, namely to make an axiomatization in which it is clearly put in evidence which axiom will drive us to classical probability and which one to quantum. This is the first step. Fourth step is in some sense was one of the latest, because conceptually is one of the deepest. And I will explain to you in more detail, but just to anticipate what problem had to be solved, let me tell you just a few words. So, the best way is still to make the analogy with geometry. But as you will see, there is a big difference, historical difference. In geometry, first, the mathematicians conceived the possibility to have more than one model for the laws of space. And decades after, the physicists understood that this different model had a physical interpretation. And so this was the birth of relativity. In probability, the converse happened. First, the physicists discovered some new model which had admirable results, fantastic results, but which was not understood. Nobody understood. As you will see from words by Heisenberg, by Feynman, by Bohr, nobody understood from where this new model came. Okay, so the first step is, can we do for probability what has been done for geometry? Namely, to understand a physical meaning. Physical means not in the sense of pure physics, but means in the sense of just reality. Well, and I anticipate the key answer, but I have to illustrate it during the talk. The key point is, first, existence of incompatible observable. This existence was first detected in quantum theory, essentially Heisenberg, individuated the famous pair position and momentum, and then with his famous X-ray microscope, essentially showed the incompatibility of the two. Incompatibility means if you want to measure with arbitrary precision one, then necessarily you will have a high imprecision on the other one. So if you want to measure position with very high precision, you will have disturbances and on momentum. And momentum will be more random. This is the famous Heisenberg indeterminacy principle. Okay. The other one was not known to the pioneers of quantum theory, and you will see has to do with the bridge between probability and statistics. In a single sentence, I can say the statistics of responses can be quite different mathematically from the statistics of passive properties. We will come back on this. So once you understand that there is this probability as universal application, not only in physics, but in practically every human activity, computer science and biology and economy and so on. So the fifth step we had to understand, and we are still at the beginning in this fifth step nowadays, is what are examples of application of non-Kolmogorov probability outside physics. In physics we know, because quantum physics is a non-Kolmogorov probability. But since now we know that these new laws of chance are universal, have a universal nature, it's absolutely clear that there should be applications outside the world of pure physics. Okay, and some research is going on, and I will try to mention when we are. The last is a little bit more technical. I don't know if somebody of you has ever heard about quantum cryptography, in which you use entangled photon to exchange messages, okay? And those of you who have heard of this, probably they have heard the criterion to distinguish the classical from quantum, which is application of Bell inequality, and to the correlation produced by quantum cryptography. And this is, we worked in 2002, from 2000 to 2003 in the first Italian concrete realization of quantum cryptography. And what we did was considered impossible by all physical literature. Namely, we did the exact computer simulation or the exact protocol of quantum cryptography. I insist on exact because if you cheat and you introduce so-called non-local elements, then it becomes a trivial thing to do. The real challenging that was considered for more than half a century impossible, and in fact quantum cryptography claimed it is impossible, namely to reproduce the protocol of quantum cryptography exactly, but with classical computing. And this is what now we call digital quantum cryptography. Digital because we don't realize it analogically as they do in the original experiment with the entangled photon, but we realize it with computer. Okay? The seventh step is a little, the first 6 steps I have tried to abstract the conceptual aspect. because as you see, each of them could be the object of a single seminar. So I have to condense it in 1 hour, and so I abstracted the conceptual elements, and I hope that I will nevertheless send a message to you that can be a stimulus to go into the more technical development. The last one is, in some sense, the most surprising, in fact, is chronologically the last, and it is the statement that quantum probability is not orthogonal to classical, but is a deeper level of classical. That is, you deduce quantum from classical. You might say, okay, you are contradicting yourself, because at the beginning you say there are new models of probability, new axioms, and now you are saying that the new model is deduced from the old. And the point is that the new axioms have to do with the conceptual framework. The last development is a mathematical framework and shows that by combination of two rather old, century-old discipline of mathematics, which is classical probability and the theory of orthogonal polynomial, you produce an enormous generalization of quantum theory, and you explain why, you will see, why Heisenberg arrived exactly to those commutation relations, and you deduce how and what are the extension of this commutation relation, which are not Heisenberg type, and why these are very deeply related to the attempt to create a nonlinear quantum field theory, attempts which have failed. And I anticipate they have failed because they were trying in the nonlinear theory to put the commutation relation of Heisenberg. But now we know that this commutation relation are an expression of Gaussianity. They characterize Gaussianity. And so if you put as an axiom, the White-Mine axiom, that the standard boson commutation relation are satisfied, you cannot go out the Gaussian. Mathematical, impossible. You will see why. So let me begin. Let me begin very quickly. Historically, in quantum theory, you know that quantum theory, after the discovery of the quantum of action, Einstein individuated gave an interpretation of photoelectric effect in terms of corpuscular interpretation of light, and shortly after, de Broglie made the converse. So like Einstein had a corpuscular interpretation of light, de Broglie proposed a wave interpretation of matter. And this was the famous de Broglie wave, and this was the historical beginning of what is known as wave-particle duality. The wave-particle duality found about 10 years after the mathematical expression into the two formalisms which were developed almost simultaneously, 1 or 2 year difference. First, Heisenberg picture, which is particle picture, because it uses QP coordinates for single. Every degree of freedom has this pair of QP, which are inspired to classical mechanics, but they are not classical objects because they are operators. And then Schrödinger was inspired by the Hamilton unification of optics with classical mechanics, and he wrote his famous Schrödinger equation, which is a wave equation. So Heisenberg was on the line of wave interpretation. But very soon, Heisenberg was Schrödinger was inspired by the analogy as I said, of quantum optics and mechanics due to Hamilton, and he really believed that there were physical quantum waves like de Broglie. However, very soon, Pauli emphasized that since most application of quantum mechanics are for many body application, in which you have many coordinates q and p, and so you have a phase space which is d-dimensional, for d that can be very high. And so he said, what does it mean? A physical wave in an unphysical space. That picture, Schrödinger picture was working very well because he was working with one particle in three-dimensional space. And so everything goes. But as soon as you are dealing with many body quantum system, Pauli objection comes in. And you understand that you cannot speak of physical wave. The physicists still nowadays use the analogy with wave, but it's an intuitive analogy. Rigorously speaking, you cannot speak of physical waves. And this was pointed out at the beginning of quantum theory. And Schrödinger cat was a kind of colorful way to emphasize the strange things that can occur if you really interpret wave as a physical wave. The wave that distinguishes mathematical occur in the quantum mathematical model with physical waves. So the result was the physicists stopped to speak of physical wave, but how to interpret now this mathematical object psi wave function? A new idea was that of virtual reality. If you read the book of Heisenberg book on physics and philosophy, you will find that he uses this term for the first time, but original idea was Bohr, and Bohr idea was there is electron which is non-measured. When we don't measure electron, it has a virtual reality in which we cannot say is a particle with a definite position and momentum, but it is a virtual reality, and if we measure position, the position materializes, and this is what is called, with a very picturesque name, collapse of the wave function. Okay. The act of measurements provokes collapse of the wave function. This collapse depends on the observable you measure, because you can measure position, but you can also measure momentum. So the collapse depends on what you measure. And this is nowadays called the orthodox interpretation. The orthodox interpretation split physicists already, and there was one front, the so-called Copenhagen school, with Niels Bohr, with Heisenberg, with Born and Jordan, and many protagonists on one side. And Einstein, Schrödinger, to mention just a few of the most famous one, on the other side. And this polemic exploded at the Solvay conference in 1927, and it exploded on what was going to become the paradigm experiment to illustrate the mysteries of quantum, the famous two-slit experiment. I just don't know if you are a mathematician or physicist, but do you know, have you ever heard of the two-slit experiment or not? No. So I think I thought I give for granted that, but essentially this is an experiment which is an idealization of an experiment that was realized in that period, the 1920, just after Heisenberg, 26, 27, by Davison and Kerner, and the so-called diffraction of electron. The idea was, if the Broglie theory is correct, that matter has wave property, then light, you have diffraction of light, you should have diffraction of light. Like that. And this was confirmed by this famous experiment by Davison and Gerner. So, so you see, this Schrödinger cat was the first of the famous paradoxes of quantum mechanics. The two-slit experiment, I have no time to go into detail, especially if you have are not already familiar with it, because there are many subtle things to be discussed. And the essential point that I want to emphasize is that the accepted interpretation by the majority of physics nowadays, which is the orthodox interpretation, so accept this idea of virtual reality. The cat is not a real object when you don't look at it. The moon doesn't exist when you don't look at it. And when you look, the collapse of the wave packets occurs. So the observer plays a role in the definition of reality. So Feynman came later, but he made an important step forward with respect to Heisenberg, because he tried to give a precise mathematical formulation of this two-slit experiment and to explain people where the contradictions are. This is very important. Again, I will, for those who have some familiarity with the debate of quantum theory, probably you have heard the name Bell inequality. Did you hear this name? Okay, and it is very interesting that from the beginning of quantum theory to the 60s, the paradigm example was the two-slit experiment to illustrate the mysteries of quantum theory. Starting from 1964, which is the publication date of the Bell paper, the paradigm changed and the Bell inequality became this paradigm. So, in fact, they are very different, the Bell inequality, apparently, because the two-slit experiment deals with probability, and Bell essentially is a formulation, a mathematical implication of the so-called EPR experiment in the Bohm version. And Bell was convinced that the inequality that he found pointed out an incompatibility between the locality principle and the possibility of having a so-called hidden variable theory. Hidden variable theory means a classical theory which reproduces the results of quantum mechanics. This is called hidden variable. Okay. As I said, the story is very long, so I cannot go in details of every. So let us fix what we have said up to now. From the beginning of quantum mechanics until nowadays, there are two paradigm experiments, ideal experiments, which are used to illustrate the mysteries of quantum mechanics. Okay, and these two paradigms are the two-slit inequality and the Bell inequality. Pay attention, they are both inequality. Even if the two-slit is not emphasized and is not known as two-slit inequality, it's known as a two-slit experiment. But mathematically, they are both based on an inequality. And now, what I want to Unfortunately, I have prepared some additional slides. So if you want to see concretely the mathematics that's behind this, you can ask me and I will show. But I made a calculation of time, and so I cannot explain all the details for everything. So I decided to give you a very quick explanation in the case of Bell, which is easier, and to slit, I reserve if you want to know. You can ask a question, some question, and I will describe this to you. Okay. So the crucial point is this. This was the beginning of quantum probability, at least for me, not the mathematical beginning. Mathematical beginning has a long history that I have no time to do, but it's long before this. But before, people were using the name non-commutative probability, which is a nonsense, because non-commutative probability, the model can be non-commutative. Okay, but starting from this moment when it was clear that the root of the two basic experiments used to illustrate the paradox of quantum theory is the same mathematical root, and this mathematical root is probabilistic. Then I think we began to change the name and to speak of quantum probability, because the quantum model comes out from something which is probabilistically different from the classical one. Now, again, let me, without calculations, tell you what is the mathematical essence of the story without writing formulas. So, these two experiments, the Bell inequality and the two-slit experiment, apparently look very, very different. As I said, the two-slit experiment has to do with the conditional probability. A beam of particles is sent to a screen. There is an intermediate screen with two slits, and the two slits can be either both open, or the first open and second not, or second open and first not. So you have three conditions, and the corresponding conditional probabilities. The Bell situation starts with the so-called EPR experiment, not in the original version of EPR, but in a later version, which was proposed by Bohm. And it has to do with two valid observables. Bohm was thinking of spin. In recent experiments, they use polarization of light. But mathematically, spin and polarization are the same. They're just a representation of the two-dimensional unitary group. So, what is important is the two experiments are very different, because they, as I said, two-slit uses conditional probabilities. Einstein-Podolsky-Rosen experiment use correlations of spin or of polarization. Now, however, they have something which is common. In both cases, you have three possible situations. So, two-slit, you have two-slit open, slit one open and two closed, slit two open and two closed. Three. Notice that they are mutually incompatible, logically incompatible. In the polarization experiment, you have three polarization directors, A, B, C. They are non-parallel. So, if you look at this in different particles, as in the so-called entangled photon experiment, you can always measure the pair correlation, but you can never measure a triple correlation. ABC are non-parallel direction, and polarization in non-parallel
direction or spin in non-parallel direction are non-commuting variable. So for them, the Heisenberg indeterminacy principle is applicable. And you cannot measure simultaneously two. But three of them, but two you can. Because one is, you can measure polarization A in particle 1 and polarization 2 in B in particle 2, because the two particles are different.
Now what happens? You have, and mathematically, what you have in common? You have in common three statistical data. In the two slit, the probability P of x given 1, P of x given 2. In the correlation, you have the three statistical correlation. AB, BC, and CA. A, B, C are the polarization direction. Okay? So these are empirical data. These are given by experiment. You have no control of this. You cannot do any assumption of this. They are data, experimental data. So what is the implicit postulate under mathematical postulate? 15? 10. Okay, I have to rush a little bit more. So the implicit postulate is that these three statistical data, conditional probability in two slit, correlation in unsampled sclerosing, they admit a collaborative. Think of geometry. Think of the birth of non-Euclidean geometry. What is Gauss' theorem egregio? Gauss' theorem egregio does exactly this. That if you have three angles, their sum is equal to pi plus a constant, which is nowadays called Gaussian curvature. Okay. So we are in a very similar situation. That, like Euclid was postulating that the sum of the three angles is pi, which is equivalent to the parallel postulate, then the fathers of quantum mechanics were postulating that this data come from a single mathematical model, but this is not reasonable. It's unwarranted, both mathematically and physics. Mathematically, well, physically, because the three situations, as I insisted very much, are mutually incompatible. So I have no way, if I want to do an assumption, I have no way to check this assumption. Second, mathematically we know that there are the famous compatibility conditions. If you have, well, okay, let me explain. So there is a famous theorem that has a very long history, beginning just with the beginning, but ended with the famous Kolmogorov consistency condition, which are conditioned on the joint probabilities so that what the physicist postulated happens. Namely, there is a unique mathematical probabilistic, classical probabilistic. But the physicists didn't know this consistency condition. They did not apply. They gave for granted that the model exists. So this is the mathematical point. So I wanted to show you how this constraint concretely happens in the Bell, in the case of the Bell inequality. But I am only at the second of the 7 points. So what I propose is that I jump this mathematical, more detailed explanation about where is the hidden assumption in the Bell deduction, which is very, very elementary, so everybody can follow. And I will try to illustrate what were the later steps, because I think for you, the last steps can be inspiring. And And so, but if they have to be inspiring, you have to at least have a vague idea of what they are. So let us conclude the first part of the development. So the second step, you individuate. They have a common probability. The paradoxes have a common probabilistic root. So it's not necessary to introduce non-locality, non-reality, virtual reality, and so on. Just to say, we are in presence of statistical data which do not admit a single probabilistic, I call Kolmogorov, like in analogy with the Euclidean model. Okay, now how? Suppose you are a scientist and you work, for example, in sociology, and you have some statistical data. Which model will you apply? Historically, all sociologists, all economists use classical models. But now we know that there are constraints. So how do you, what can you do scientifically to solve this problem? Well, okay, in geometry, I gave you the example of the Gaussian curvature. Gaussian curvature is fundamental because it's the first example of statistical invariance. Now we know a lot of examples of geometrical invariance, but we didn't know at the beginning of quantum probability the statistical invariance. Statistical invariance, what are statistical invariance? The statistical invariant answer the following problem. If you have a set of experimental data, statistical measurements, correlation, conditional probability, whatever, joint probabilities, then how do I decide if I have to use a Kolmogorov model or a non-Kolmogorov model? Okay, I have also prepared some example done many years ago, 1981, in which we computed the statistical invariant in some interesting case. And what we found is not trivial because they are related to also with geometry in a non-trivial way. But so I hope the third point leaves this message clear. See, in geometry and probability, the situation is very different. In geometry, we have angles. We measure angles. In probability, we measure, say, conditional probabilities, which are the most general. Then, these measurements impose constraints on the mathematical model you can use. And these constraints are mathematical, and you can deduce. Okay, I will jump. Okay, I jumped this. Okay, what are the hidden axioms? You see, the only thing I want to, for a reason of time, I cannot go in big detail, but there are some important things that I think every person who does mathematics or science should know. First of all, is what is the difference between an axiomatization and the mathematical model? Okay. This difference, I think, is best pointed out in a paper by Hilbert, von Neumann, and Nordine, who say the following. I want an axiomatization to be model independent. The good axiomatization should be model independent, and the mathematical model should be deduced from the axiom by deductive steps. So this is the fundamental point. Many people still nowadays, when they speak of these problems, they make a mixture, confuse mathematical model and axiomatization. But if you want to go deep in the understanding of a theory, you have to keep the two well distinguished. Okay, so mathematical model of quantum probability. There were many already immediately. The so-called partial Boolean algebra, partially ordered set, von Neumann algebra, sister algebra, operator algebra, many. But the problem is, just I mentioned here, Kolmogorov model, not an axiomatization in the sense that we discussed. It is a description of the mathematical model. There have been attempts to do axiomatization, but not so in probability, but I will not discuss them because they are not very satisfactory. Okay, so the problem was to do an axiomatic that now unifies the two models, the classical and the quantum model. And this is very interesting. It is an answer to one of the famous 23 Hilbert problems, which were posed in International Mathematical Congress of 1900. The sixth of this problem Hilbert posed is this: to treat axiomatically those physical disciplines in which already today mathematics plays a predominant role. These are, in the first place, the calculus of probability and mechanics. So this was 1900. Notice the historical connection, the historical event. 1900 is exactly the same year in which Planck discovers the Planck constant and gives birth to quantum mechanics. With this discovery, the two disciplines mentioned by Hilbert are unified with quantum mechanics, which is a new mechanism and a new probability. Okay. So the fact that there was a new probability calculus was immediately recognized. As I said, the first paper who tried to describe is a paper which comes from a seminar in the Hilbert, proposed by Hilbert and co-authored by Hilbert, von Neumann, and Nordheim in 1927. So you see, very almost simultaneous with the Schrödinger paper, 2 years after the Heisenberg paper. So it means at that time mathematicians were sensitive to what was happening around them. Nowadays, I am afraid they are much less. But I think we should go back to this tradition, the good tradition of mathematics, to look around. 5 minutes.
Take 5 minutes.
Huh?
It's time, but you can.
It's time. Well, I already mentioned that the Bayes, why the Bayes axiom plays the role of parallel axiom, you understand very well with the two-slit experiment. I have no time to discuss this now, but the two-slit really gives you the deep understanding why underlying Heisenberg and Feynman and Bohr, all these people reasoning, there was this. Okay, this is an axiomatization of probability. I think this is a more technical, but this is an important point. So I already mentioned in the introduction, I will not have time unless you ask some example to describe to you. But what you have to remember is this: the statistics of responses can be totally different from classical statistics of passive probability. The symbol of classical probability is urn, a box with balls, red and white, and you extract
when you extract a ball from the box, you read the color, white or red. And for centuries, we give for granted that the color we read is the color that was in the box. Take a chameleon, not a ball. The chameleon, what is its color? If you put it on a leaf, it is green. But if you put here, it will, say, the idealized chameleon will become brown. So imagine that you have a closed box with a chameleon. An experimentalist wants to keep him out of the box. So he puts some food on a leaf. And he says the chameleon is green. So why chameleon is so important? I wrote a book called Urns and Chameleons. Urn is the explanation of classical probability. Chameleons is the good metaphor for quantum. Because when you speak with a physicist friend and you ask them to describe their experiments, they are much more similar to the experimentalist who puts a food on the leaf and wastes the response of the chameleon, rather than the passive extraction of a property that is in. Physicists do experiment by measuring reactions, so responses. Reactions to interactions are typical responses. And this is the statistical result. That is why when you do statistics of atom, you find a new probability, because it's statistical responses. Okay. Okay, outside quantum physics, I will jump. And now it's time to break, and we begin the second part, in which we go in the opposite direction of all what I have said now. Namely, in the second part, I will try to show you how the quantum formally is a deeper level of the classical one. But so, let us have a break now.
So we'll take a break, a tea break, and then we'll resume after 5 minutes. Yeah, the tea has arrived here. Please help yourself. You would like to have tea?
Yes, with pleasure. Thank you.
It's a sweet tea. Sugar.
Sorry, I did not give enough time, but fortunately,
Yeah, some
not
time.
automatic. Yeah, but now I have to speak on the last one. That will more emotion.
So we have some 70 people who joined online. Yes, 70 people who joined online.
So it was very good idea.
Yes. Okay, we can start. We'll resume the session.
Okay. So now the second part. Second part will be, as I said, that the chain of reasoning was from the so-called apparent quantum paradoxes to non-Kolmogorov probability as explanation, then statistical invariant, then unified axiomatization of classical and quantum, and then the what I call the digital quantum cryptography, the example which was considered impossible in physics to have deterministic, reversible system, classical system, reproducing exactly the EPR correlations, and in a way compatible, completely compatible with locality. But, as I said before in the introduction, you cannot exclude that you have an extension of the classical theory in which the extension is embedded, but canonically. In mathematics, the word canonical was introduced by Bourbaki to mean something very natural, non-artificial. And there is no precise definition of what is canonical and what is not. But if you have some experience, you acquire this feeling. You immediately recognize a Baroque construction full of artificial assumption from a theory in which you only deduce. Now, in fact, what I want to show is that we can deduce the classical, and this is a development relatively recent, about 20 years, but is the field is so wide that we are just at the beginning of our understanding. So the main question we will answer is this. This is a question which has plagued those who for working in quantum mechanics since the very beginning. And the question is, from where do the Heisenberg commutation relation come? He found, if you look at the original paper by Heisenberg, this is a wonderful paper, and you really understand how a genius can go through pure intuition, trial and error, and deduce. In fact, he didn't write explicitly, but implicitly there are these commutation relations, and he deduces them from Fourier development of solution of a classical equation of motion in classical. So you see, really, he himself did not understand how this came out. At that time, physicists didn't know that there exists in mathematics non-commuting objects like matrices. It was Born who discovered this when he traveled in MIT and discussed with Wiener, who explained to him that there exist these objects, they are called matrices. And then many people began to speak of matrix mechanics, because for them, non-commutativity means matrix. Okay? So the problem is, from where do the commutation relation come? Is there a natural explanation? Not baroque, artificial, nature. That you will judge nature, not the authors of this. So, as I said, Heisenberg himself claims that the mechanism, the formalism of quantum mechanics is far from intuition. And this was insisted many, many, many times. In fact, even without insistence, you can understand that there was a feeling of unsatisfaction in scientists from the huge number of papers devoted to foundation of quantum mechanics. No comparison with the papers devoted to foundation of classical mechanics, because foundation of classical mechanics is intuitive in the sense of Heisenberg, but quantum is not. And so people felt the need to go deep in the foundation, to try to understand this apparently incomprehensible mechanism. And more than 50 years after Heisenberg, a very famous mathematical physicist, Edward Nelson, gave a famous aphorism, now famous. He says, second quantization is a functor. If somebody of you knows about the Fock functor, he was thinking of that. And first quantization is a mystery. And what I want to try to convince you is that no longer mystery exists. Now we really understand from where the Heisenberg commutation comes. Okay, I will speak about application later. I only discuss the case of one variable, which in physical language means systems with 1 degree of freedom, which was originally Heisenberg was considering this. So let me recall very briefly some notations of classical probability. I will denote by X a random variable, mu, the probability distribution, real valued random variable. For me, in my talk, only real valued random variable I will consider. And mu, the probability distribution, which is since the variable is real valued, is a distribution on R. When I speak of random variable, I always suppose that it takes all moments. So this restricts the class. But we will see that it is rich enough. Okay? And moreover, I use the notation mu for the integral of the probability distribution and for the measure, because I want to anticipate the algebraic notation in which mu will become a state on a star algebra. Okay? So I use the same symbol for the measure mu and the associated integral. Then I take one of the most famous objects of mathematics, which is the algebra of polynomials, in the term one bar. Well, for me, polynomial means polynomial function. So I can speak of variables instead of indeterminates. Okay. So I take the polynomial functions on R, but with complex values. So since the measure mu as all moments, remember mu is the distribution of the random variable x. So every polynomial is integrable. And therefore, the measure mu gives a state on the star algebra of polynomials. The polynomial is a star algebra. You have standard multiplication by polynomial, standard addition, and the involution is given by complex conjugation. With these three operations, it becomes a star algebra. And so if I have, remember that a state means a positive linear function normalized so that the expectation of the identity is the identity. This is the definition of state in general terms. Any state defines a semiscalar product. Semiscalar means that zero norm vectors are allowed. And the semiscalar product is the natural generalization, algebraic generalization of the standard L2 scalar product. Okay, this is L2 of the measure mu and the scalar product, and this is the algebraic formulation, natural generalization. Okay, but in my talk, many technical subtleties arise when you have zero norm vector. So to follow my talk, you think that this is not zero. The of a scalar product, which means that the norm of a polynomial is zero if and only if the polynomial itself is zero. Okay. Now, what happens? What are the simplest polynomials? Of course, the monomials, because any polynomial is a linear combination of monomials. Now, we have a scalar product. The monomials, in general, will be linearly independent, but not orthogonal for the given scalar product. So, we orthogonalize the monomial without normalization. What does it mean orthogonalize? Since we have a space with a single orthonormal basis xn, the monomials are a linear basis. So you simply subtract to the monomial. Here I have an error I have to correct. Otherwise, sorry, but no. This is an error. Okay. Sorry, this is here. It was written Pn, not Pn minus 1. You subtract to the n monomial its component on the subspace generated by the monomials of degree n minus 1. So what remains is the essentially n degree with respect to the scalar. Okay, this is a this sequence Pn is this is the famous sequence of monic orthogonal polynomial. Why monic? Because you see, this is a projection on space generated by monomials of degree n-1. So it is a polynomial of degree at most at -1. So the highest degree is xn, and it has coefficient 1. Such polynomials are called monic. And now, the bridge with analysis. 150 years ago, Carl Gustav Jacobi proved a relation which is simple to prove. You can do an exercise to ensure you will be able to do. Because it's simple, there are in mathematics things which are simple but are enormously big. Simple things are many, but to single out those simple things which are very big, then you need some real thing inside of you. And Jacobi had. And he found this relation. If I multiply the nth polynomial by x, a priori, I can find a linear combination of all other polynomials. But in fact, in this linear combination, only 3 factors enter. So this x times phi n x can only have components on the polynomial degree n+1, polynomial degree n, and polynomial degree n-1. This is the famous Jacobi three-diagonal relation. You see why three-diagonal? Because the diagonal is n itself, the component of xn on phi n. And then they had the lower diagonal, if you think of this as a matrix, which is phi n -1, and the upper diagonal, which is phi n+1. So that is why it's called three-diagonal relation. Okay. What is alpha n and omega n? Alpha n is an arbitrary real sequence. Omega n is a positive sequence which satisfies a certain condition. I will not have time to explain now. Maybe this condition is a very deep quantum interpretation. Just I mentioned, this condition for the analyst for 150 years was just Jacobi condition. Now we understand this condition is necessary, sufficient condition for the fact that the creator is an adjoint. In quantum interpretation, you will see this. 70 years after Jacobi, Favart, French mathematician, proved the converse of Jacobi theorem, which is very important. Namely, he proved that if you give a pair of sequences, alpha n, real numbers arbitrary, omega n, positive, and satisfies that condition that I mentioned to you, if some omega k is 0, starting from that k, all omega k must be 0. This is the definition of principal Jacobi sequence. Then there exists a probability measure such that when I consider the orthogonal polynomial associated to this probability measure, I find the Jacobi relation with the given sequences alpha n and omega n. Okay? So Jacobi goes from mu, probability measure, to pair of sequences, alpha n, omega n. Favart goes from pair of sequences to mu. And the bridge between the two is the Jacobi relation. Okay? I cannot enter into this, but if there is among you some statistician, I think this is a very important thing to go into, because statistics is fundamental, for example, for artificial intelligence. And now we have a much more powerful mathematical tool for statistics, which is what I'm trying to explain to you. Now, let us do just a change of point of view. We don't change the mathematics. We only change interpretation. The Jacobi relation is a relation between functions. I multiply a polynomial by x, and I obtain a linear combination of three polynomials. But I can introduce, as we do, this operator is very well known in quantum mechanics. It's called the multiplication operator by x. You can define multiplication operator by x like this. Now, you can define another operator. You see, the first term is phi n plus 1. But the phi n is an orthogonal basis. So I can define arbitrarily a linear operator on each phi n, and then extend by linearity. Okay? So the operator A daga is uniquely defined, and I call creation operator. It increases by 1 the degree. Then, remember the Jacobi relation. There is the preservation term, n. So I define an operator A0 phi n, by definition is preservation. Sorry, this is again an error. It should be n, not n minus 1. Sorry. So you see, preservation operator, called preservation because it preserves. It just maps phi n into a multiple of itself. And annihilation, like creation, increases the degree by 1, annihilation decreases by 1. Okay? Now, the functional Jacobi relation, in operator interpretation, what becomes? Becomes that x phi n, the operator multiplication by x applied to phi n, is equal to A daga applied to phi n, creator, preservator, annihilator, all to phi n. But phi n is an orthonormal basis. So if two linear operators coincide on an orthonormal basis, they can be unbounded, but they coincide on the domain spanned by this. Which is the domain? All the algebra of polynomials. So we have finally what we call this identity. But x, what is x? Was our classical random number. And was arbitrary, except for the fact that it has all moments. So what we have proved, just by changing interpretation. Nothing more. You see, I see when I insist on the fact, no artificiality, nothing put by hands. Everything is deducible. We have proved that every classical random variable with all moments has a microscopic structure because it is the sum of three objects. I call creator, annihilator, and preservator because I am inspired by quantum mechanics. Okay. Moreover, the preservator is Hermitian operator equal to its adjoint. And as I said to you, the condition that was found by analysts purely algebraically as that is if some omega n is 0, all omega k for k greater or equal to n must be 0, is equivalent to say that the creator is an adjoint and the adjoint is the annihilator. So we have a picture that begins to look like the usual picture of quantum mechanics. But, as you will see in a moment, X generates a commutative algebra because it's a standard polynomial algebra. But the microscopic elements that compose X do not commute. But do not commute is a negative statement. However, we begin to understand that non-commutativity arises natural from classical probability. But we will see. Now we go to a much more precise statement. Not generic non-commutativity. We will have very precise non-commutativity. In fact, we will have even more than commutation relations. We will have a table of multiplication. Let us see why. So remember the quantum decomposition of the random variable, which is equivalent to the Jacobi tridiagonal relation. Remember the definition. I only speak of creation and annihilation because preservator is simple, but I want to arrive very quickly. I have not so much time, so I will not discuss A0. So you see, A daga increases the degree by 1, and A decreases and multiply by omega n. So let us apply A minus A plus to phi n. According to this definition, I have A minus not applied to phi n, but phi n plus 1. So I have omega n plus 1. But if I do the same in the reverse order, I first apply A minus, then I apply creator. You see, here I have omega n, phi n minus 1. Creator simply increase. I have omega n. And so if I subtract the second from the first, I obtain a commutator. And this is a commutation relation. This is true for every n. This is true for every n. Now I want to do as we did with the Jacobi relation. I want to write this commutation relation as an operator identity. But here I have a dependence on n. See, I apply on phi n, and this coefficient depends on n. So how do I do? Simply, I introduce another familiar object for those who know some physics, which is called the number operator. The number operator is the unique operator which, applied to the n-orthogonal polynomial, multiplies by n itself. So Pn is eigenvector with eigenvalue n. This is called the why it's called number operator, because its eigenvalues are the natural numbers. Okay. So if I have an arbitrary function from the natural integers to the complex number, I can define f of this function applied to n by fn. So this is, you can call spectral theorem, but it's much more elementary. Okay. Okay. So with this definition of f lambda apply, operator f of the function of the number operator, okay, the commutation relation that we had deduced, this is the generalized boson commutation relation, becomes a true operator identity. And you see, this begins to remind you quantum mechanics. What is the difference? In boson quantum mechanics, this commutator is a scalar. The right-hand side is a scalar. But here we have an operator, but a very special operator, a function of the number operator. Huh? So, we have proved that every classical random variable with all moments has its own commutation relation, has its own creation, annihilation, and preservation operator, and its own commutation relation. And you obviously may ask, okay, what can you say about Heisenberg? theorem. The theorem is this. Given a strictly positive number, pay attention, strictly positive, well, there is many developments that I have no time to say, but here we will take strictly positive. Given a strictly positive number, h bar, I call h bar to remember you the standard commutation relations, there exists a unique symmetric classical real-valued random variable whose canonical commutation relation are the Heisenberg one. And this is the Gaussian. So you see, it's not, in some sense, a posteriori, not by chance that Heisenberg fell into this commutation relation, because they are the commutation relation associated canonically to the most important measure in probability, which is the Gaussian. So the Heisenberg commutation relation in the new interpretation of Plato are nothing but the canonical commutation relation of the Gaussian class. Why I say class? Because you see, in the theorem, I say that the Gaussian is the unique symmetric classical random variable. And why? In the commutation relation, you see only omega appear, not alpha. Only the principal Jacobi sequence. It means that if two probability measures differ just in the alpha n, they will have the same commutation. A and A dagger will have the same commutation. It happens that the Gaussian measure and the Poisson measure have exactly the same principal Jacobi sequence, which are the multiple of these. So this theory already explains to you something that was discovered in many different contexts, namely that the Wiener space and the Poisson space are isomorphic. But now we understand they are isomorphic. Why? Because Wiener and Poisson, Wiener is Gaussian, Poisson is Poisson, and they have the same principal Jacobi. The only difference in the second. So they have the same commutation relation. The commutation relation uniquely determines the first. So we can already explain something that for the physicists was not obvious. But now we can know the deep root. Well, the proof I have put, because it's very simple. From the commutation relation, if you want that a commutation is a constant, is a number, by simply you writing down the explicit commutation relation, and you remember how we wrote on the commutation relation applied to the n orthogonal polynomial, and then you have an inductive relation on the omega n, because the difference is constant. So it means that omega n plus 1 is obtained from omega n just by adding n, constant. And then you get that omega n plus 1 by iterating is n plus 1 times a positive constant. This positive constant, with a simple calculation, you identify with the covariance. But this is exactly by a known theorem in the theory of orthogonal polynomial. This sequence omega n characterizes the Gaussian among the symmetric measures. There is only one measure which has this principal Jacobi sequence, which is symmetric. And this is the Gaussian. And so we have proved that the Heisenberg commutation relation appear if and only if we are in the Gaussian class. And this is the theorem that we used. Now, as you remember, when I have shown the original Heisenberg commutation relation, they were not on A and A dagger, but they were on P and Q, position and momentum. So we have the analog of position, which is what? What is the we know it's the multiplication operated by x, the random variable, the coordinates. It's the same definition as in usual quantum mechanics. Okay, what is the analog of momentum? It turns out that the analog of momentum, this is rather subtle because it has to do with the complexification. We started from a real Hilbert space. Remember, we consider real valid random variable, but we consider complex polynomial with complex coefficients. So we have an embedding of the real polynomial into the complex, and we can complexify this embedding. In this complexification, the momentum arises, but only for symmetric real valid random variable. Symmetric, I don't give you the precise definition. What here is meant is so-called moment symmetric. It means all the odd moments are zero. Symmetric, the Gaussian, for example. Centered Gaussian is symmetric. The odd moments are zero. Huh? So a non-symmetric random variable has no momentum, but symmetric it has, and it has this form. Why do I claim that this is the good definition of momentum for an arbitrary classical random variable? Well, because I have the following commutation relations, the following theorem. So you see, this is for arbitrary real valued random variable, and these are the original Heisenberg commutation relation. When the delta, what I call delta omega lambda, remember delta omega lambda means omega lambda plus 1 minus omega lambda. It's a difference operator. Delta, partial delta is a difference operator. Okay? So you see that when we have the Gaussian case, which is Heisenberg, we get the original formulation of Heisenberg. Eh? Px means, by definition, this. Minus I, A minus A dagger. Here I have to check the sign, put a quotation marks on the minus I, because it depends on the convention. There are different conventions. And now I don't remember if I took the most convenient one here. Okay, but it's a minus sign. It's easy to correct if we need. Okay, so you see, this is a non-trivial fact. This is something new for classical probability, and new, but which has a very deep implication. And here we should exercise our fantasy. Why? Because, you see, physicists have a very clear interpretation of what momentum is. Because Heisenberg arrived to momentum generalizing the standard momentum of mechanics. So in the Gaussian case, what we find, Gaussian case means this. You see, Gaussian case is the second one. H is constant. This delta omega lambda is a number. Doesn't depend on lambda. Just close. This characterizes the Heisenberg commutation. Okay. But if we have the more general situation, so, and moreover, you know that this is what is momentum is an intuitive interpretation, because it generates translation on the functional position, you know. Now, what is momentum for a general number? See,
Not mathematically we know. Even if you see, the algebraic formula is simple, but analytical can be deep. For example, a recent paper we have with Yungang Lu and Tarek Hamdi, we calculated the momentum in the simplest possible non-Gaussian random variable. The semicircular random variable. Somebody of you maybe heard about free probability or not. But semicircle is the Gaussian for free probability, and we calculated the momentum for semicircle, and it turns out to be the Hilbert transform with respect to the semicirculation. So you see, non-trivial. It's an interesting result. But it goes in the philosophy. I'm trying to illustrate to you. Everybody who applies probability has to learn to exploit these powerful tools. The physicists exploited in physics, in quantum mechanics. But now we know that these tools are not proper to quantum mechanics. They are absolutely universal for people. And so we have to learn. For example, we have the mathematical formula, but probabilistically, what is the momentum for non-Gaussian case? Okay. In the boson case, Heisenberg, we know momentum is the generator of translations, and is very intuitive with the bridge between momentum and velocity, because momentum is translation, and the generator is infinitesimal translation of the velocity. So the bridge is very intuitive. But how do we make a bridge for this generalized momentum? That is why I say we have humbly to begin with the simplest random variable like semicircle, and to try to understand in these cases. Then we will maybe generalize, you see. But this is not an abstract generalization. This is something very canonical. This is also nice, because you see, take an arbitrary state. We know we can apply the standard argument, but originally, historically, this is due to Hermann Weyl, that non-commuting observables always satisfy an indeterminacy principle. Okay? And in fact, you prove that for arbitrary state, you have a random variable, and there is this that physicists believe was proper of quantum mechanics, but this is not true. If P is the conjugate momentum of the classical random variable, which is also an observable, because it is a self-adjoint operator, so spectrum is real. So it's observable according to standard interpretation. It has a, well, and if we choose, well, I didn't put here. Okay. So if we have momentum, which is the analog of the boson momentum, then the p square divided by 2 will be the analog of kinetic energy. So we have the Hamiltonian. While p is usually not bounded below, p square is positive, because it's the square of a self-adjoint operator. So interpretation as energy is well justified. And we have the explicit form, for example, in the semicircle case, it makes a very beautiful bridge with classical harmonic analysis. We express the evolution in terms of Jensen function of the second kind. So we have position, momentum, kinetic energy. We have all quantum mechanics for any random variable, which is classical and real variable.
Well, let me conclude. You see, what is the fundamental new message? The new message is quantization is not specific to physics. If you remember the first part of my talk, I was saying, let us look for application of quantum probability outside physics. And that was conceptual part. But this is mathematical part. We discovered that there is an ubiquitous, wherever you have probability, of course with all moments, you have quantization. And this is an important new point. We have to understand how to use it outside physics. This is a conceptual problem. That, however, is a challenge. Mathematicians should not only consider technical problems, I think. Conceptual problems can be the source for very deep and beautiful technical problems. And in fact, this is what I say is the open challenge that I just said. Okay. But since we have to learn, for example, what does it mean quantum correlation in biology, in economy? We have to learn these things. And but this is for the future. I did not mention that. So you may say, okay, what happens in multi-dimension? I discussed everything for one, remember, one variable, real variable. What happens is I have a vector variable. And you know that the quantum field, a classical field, stochastic field, is a vector variable with values in infinite dimensions. Okay. All the theory completely goes. The characterization of Gaussian, all goes. But there is one thing that changes deeply, and that has to do with the Favart dilemma. The theory is more complex. It's no longer true that the preservator and annihilator are independent. Annihilator, remember, is the principal Jacobi sequence in one variable, omega n. The point is that there is no good analog in multidimension of omega n and alpha n. They become operator. Alpha n is a real number. It becomes a self-adjoint operator in multidimension. Omega n is a positive real number, and in multidimension becomes a positive definite character, which is a more complex object to start. Okay. However, we have a lot of there is one case in which there is one class of measures for which the multidimensional case becomes very simple. Which is this class? Is the class of measures. Remember, we are speaking of measures on Rn, a real valued Rd, a d-dimensional real value, real vector space. Okay. Then, on this real vector space, you have linear transformations. And think of the Gaussian as your main example. What is the fundamental property of the Gaussian? Every Gaussian in multi-dimension, by a linear transform, multi-dimension means that Gaussian is a measure on Rd. So it has a covariance which is a d by dimensions. Huh? By diagonalizing the covariance, you reduce the Gaussian to a product measure. So the Gaussian has this property. There exists a linear change of coordinates in the real vector space such that the transformed measure is a product measure. For this,
all the theory that we have. Now, you know that the physics, the quantum commutation relation, the CCR, the boson commutation relation, characterize Gaussian. So all the quantum field, if physics is used, enter in the one-dimensional field. Because they are Gaussian, so they are reducible to product. And the big challenge we are studying since many years, that is hard mathematics, is let us go beyond this class of issues. Let us study the theory of what is the next step after the Gaussian, in which you have not the factorization. That is not linearly equivalent to a product measure. Because in physics, product measure means there is no interaction. So they are not so interesting system. In physics, you want interaction because all the physics is included in interaction. So that is why we call this program nonlinear quantization. Okay. Nonlinear in the sense that it is, for example, if you take the Gaussian and you take the square, then you obtain a famous class of probability measure. But the single Gaussian, you get the gamma. But if you go into from the point of view of orthogonal polynomial, you obtain a class which is called Meissner. And that is the candidate we are pursuing for the simplest nonlinear quantum, the quadratic quantum. But non-problem. It must be non-problem. If you want product everything this is in fact what the physicists have done up to now. But we want to go beyond. We want to do the non-linear quantization, which means quantization for non-product measures. And okay, with this, I think I finish. I did some calculation to show you the variance, but I think they will not add very much to what I already told you. The Fermi case I will not even mention. The appendices are the example I began to do and I couldn't do to slit and the Bell inequality. Where is the hidden assumption? If somebody wants to know, otherwise I can leave my slides and you can, if you are curious to see in the argument of Bell and the slit experiment, where precisely the hidden assumption arises. You can make it. So thank you for your attention, long attention.
Any questions for the speaker?
For you, quantization is non-commutativity.
What?
Quantization means non-commutativity. That's what for you quantization.
It is much more precise. No, quantization is more than we have the full table. So you start from the polynomial algebra, which is coherent. And then you associate the polynomial algebra, not of x, but of a and a0. And this is the analog of what the physicists call the CCR algebra for Bose, the CR algebra for Fermi. So this is the standard quantum field. We have the second quantization function, generalized in this general quantum mechanics. So it's not simply non-commutative, the whole structure. The whole structure of second quantization. You know, they call second quantization the physics because the name second was born in because they were thinking of the quantum physics. So they were quantizing a Hilbert space. The Fock, I don't know if you know what is a Fock space. No. So it's a little bit delicate to explain what is second quantization. But let us say that if you study this approach, what you are doing is generalization of second quantization.
Here there is this assumption that you have all the moments which are bounded, and that helps you use the Jacobi thing with the polynomials, right?
That not all variables. This is something we have tried for many years to do, but you need a new idea, a good idea. I have one example with no moments or with only few moments, and these are the infinitely divisible. For them, there exists what I call the Kolmogorov-Araki-Wundt-Araki-Schmidt theory, which makes a natural bridge with the force. But they also have a quantum, but it's not a canonical. It's more sophisticated and very strictly related to infinity. So the answer is there are some measures, random variables which have no moments, which have a quantum level. But that quantum decomposition is not the analog of the canonical. Is another.
Does this fall under this, the ones which have tails, they do not have moments which are bounded? You know, this distribution which have tails, I think. Like,
Yes, yeah, the typical distribution without moments. For example, the stretched exponential.
So this,
E to the minus f to power r, fractal Brownian notes, they are all invisible that way.
and there is quantization for those or for that class?
There is a quantization from that. That is from that, this goes back to Kolmogorov. That was generalized for the case of one real variable. Araki, Woods, and other physicists generalized it to random variable with values in arbitrary legal. So the essential idea is that infinite indivisibility is strictly related to the Fock construction. It's a thing that comes up. The Kolmogorov paper is before the Fock, so he doesn't use the language of quantum mechanics. But he goes spirals in the universe space. It's called the wave, and it deals with stationary processes and infinity. But then it was recognized by Araki that there is a range with the Boson quantities. Then is more subtle, and also is very interesting. Very interesting.
People attending online. So the people attending online, do they have any question? You may raise hand. I don't know. That's the battery.
They say it's battery,
They're
but it's
still there,
strange because it should charge. I don't understand why it doesn't charge.
Okay, maybe I don't see anybody raising hand here. So I have one question. So you spoke about application of quantum probability to areas